Assalamualaikum warahmatullahi wabarakatuh. A very good day to all of you. So in part number 4, which is referred to the previous part, we already discussed about the Exergy and also Exergy change for the closed system. So we already derived the equation for Exergy and also the equation for Exergy change for a closed system. So now in this part we will discuss about the Exergy and also Exergy change for the open system. Okay, so for part number 5, we will learn about the Exergy of a flow system. So at the end, we will derive the equation for Exergy and also Exergy change for the open system. So this system, instead of a flow stream system, we also can call the system as the flow system, stream system, or open system. Okay, so similarly, we need to before we derive the equation, we need to analyze the system by using our reference equation, which is energy balance equation that we have learned before. E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equal to delta E system. Okay, so now we want to derive the equation for delta X system, which is referred to the Exergy change of a system for the open system. So now we need to manipulate the term or the equation for delta E system. This is our base equation. Okay, for closed system, we know that energy change for the closed system or non-flow system. The schematic diagram shows the example of the closed system. So we already know that the formula for delta E for closed system equal to delta U plus delta KE plus delta PE. So internal energy difference plus kinetic energy difference plus potential energy difference. However, if you look the formula for energy change for the open system or for the flow system, the schematic diagram shows the schematic diagram of a system that allow mass in and also mass out to the system, which is referred as the open system. Okay, so the dotted red line represent the boundary of the system, and the system normally we consider as the control volume CV. So let's say we have a mass of fluid or a mass of substance with pressure P and also volume V. So in order to transfer the mass into the control volume, so we need to supply an energy to force the mass to enter the control volume. So this kind of energy we call flow work or W flow. Okay, where the formula for W flow equal to PV. Okay, similarly with mass out process, where if you want to to allow mass come out from the system, from the control volume, okay, still we need to have to use energy that we call flow energy or flow work. Okay, W flow. Okay, so now if we implement this concept, so we will have the formula for delta E for the open system actually equal to delta U, internal energy difference, plus V delta P plus delta KE, kinetic energy difference, plus delta PE, potential energy difference. Okay, so the term for V delta P, actually if you look in the schematic diagram, this term represent the flow energy or flow work that we discussed in the schematic diagram. Okay, and we know that based on our thermodynamic 1 knowledge, basic knowledge for the enthalpy, the enthalpy formula H equal to U, internal energy, plus PV, pressure multiplied by volume. Okay, so if you combine the term for delta U plus V delta P, this term actually represent the enthalpy difference, H, delta H. So instead of we have delta E for open system, delta U equal to delta U plus VAP plus delta KE plus delta PE. So we will have new equation for delta E for the open system, which is equal to delta H, enthalpy difference, plus delta KE, kinetic energy difference, plus delta PE, potential energy difference. Okay, so now if we compare the formula for delta E for the open system and also delta E for the closed system, the difference is the delta E for open system will use delta H, enthalpy difference. However, for delta E for the closed system will use the internal energy difference, as shown in the slide. Okay, so that's the difference. Okay, now we will derive the equation for exergy X and also exergy change delta X for a flow stream system or for the open system. So in previous slide we already learned that the formula for delta E open system equal to delta U plus V delta P plus delta KE plus delta PE. So if we rearrange the equation, so we'll get this equation where delta E open system equal to delta U plus delta KE plus delta PE plus V delta P. So delta P here refer to the pressure difference. Okay, so if you look to the schematic diagram that we have already discussed before for the open system, so the term for V delta P actually represent the value or the formula for workflow, which is equal to PV, and the pressure in this equation normally based on the absolute pressure PABS multiplied by V. So now if we consider or relative our condition to the environment condition, where we consider the exergy concept, so instead of W flow we will have X flow, the maximum potential of W flow. So X flow will be equal to P minus P naught multiplied by V. So P in this equation for X flow represent the gauge pressure. So the gauge pressure minus atmospheric pressure or environment condition multiplied by volume. Okay, so now if we consider maximum potential of energy, or we consider exergy concept, so from the equation of delta E for the open system, we will have the equation for exergy. Okay, so we have XF, exergy for the flow system, or exergy for the open system, based on the formula for delta E for the open system, will be equal to X and F, the exergy for non-flow system or exergy for the closed system, plus X flow. Okay, the exergy what I call the maximum potential for the W flow. Okay, for the flow work. Okay, so if we look from the what I call the basic equation for delta E open system, so delta U plus delta KE plus delta PE in the equation represent, if we analyze by using exergy or we consider maximum potential of energy, so this term actually refer to the X and F. So exergy equation for the closed system or non-flow system. And the term for V delta P, if you consider maximum potential of the energy, so we'll have the term for flow exergy, X flow. Okay, so if we elaborate this equation, so we can get the equation for XF, exergy for the open system. So where we have U minus U naught plus P naught multiplied by V minus V naught, volume difference, minus T naught multiplied by S minus S naught, entropy difference, plus the term for kinetic energy and also the term for potential energy. So we have additional terms if you compare to the previous what I call the formula for closed system. For open system we have additional term P minus P naught V, the term for X flow. Okay, Okay, so this equation refer to the equation for x and f, and the last term in the xf equation represent the equation for x flow. So we know that enthalpy formula H equal to U plus PV. So we if we look in the xf equation, we have the term for U, internal energy, and also the term for PV as shown in the slide. So if we combine this equation, if you combine these terms, so we can, instead of we have U and also PV parameter in the equation, so we can change with the enthalpy parameter. So now we have the complete I call equation for Exergy for the open system or for the flow stream system, which represent by using the symbol XF. So Exergy for the open system, XF equal to H minus H naught enthalpy difference based on the environment condition minus T naught multiplied by entropy difference based on the environment condition, plus the term for kinetic energy and also the term for potential energy. So the unit will be kilojoule. So we have kinetic energy terms, potential energy terms, enthalpy different terms, and also entropy different terms for Exergy equation for the open system. Okay, so if we consider Exergy per unit mass, so we have this formula where we have 5. In terms of symbol, we call this symbol as 5 equal to xf divided by m equal to specific enthalpy difference minus T naught multiplied by specific entropy difference plus the term for kinetic energy and also the term for potential energy, and the unit will be kilojoule per kg, because the formula actually is the formula equal to xf divided by mass. Okay, so now in order to obtain the formula for delta xf or Exergy change for the open system, so we just subtract the Exergy equation at the final state, and also the Exergy equation for the open system at the initial state. So so now we have the formula for delta xf, which is equal to m multiplied by 5.2 minus 5.1 equal to m multiplied by bracket h2 minus h1 minus t naught s2 minus s1 plus the term for kinetic energy difference and also the term for potential energy difference. So now in this, the equation for delta xf, so in the equation don't have any parameter for h naught and also s naught in the equation, because during the subtraction of the xf equation for the final state and also initial state, we already eliminate the term for, or the parameter for h naught and also s naught. Okay, so now if we simplify the equation by neglecting the the effect of kinetic energy and also potential energy, so we will have the final or simplified Exergy change for the open system. Okay, so we have delta xf equal to m multiplied by enthalpy difference minus T naught multiplied by entropy difference. Okay, so in terms of formula for Exergy change, so we already derived for both, for closed system and also for open system. Okay, example 1.8. A 200 meter cubic piston cylinder device contains compressed air at 1 megapascal and 300 Kelvin. Determine how much work can be obtained from this air if the environment condition are 100 kilopascal and 300 Kelvin. So when the problem mentioned about the environment condition, so this question will involve this with the Exergy, the maximum potential. So now first we need to identify whether this problem involves open system or closed system. So now the system involves piston cylinder device. So the piston cylinder device actually refer to the closed system. Okay, so the volume in terms of compressed air inside the cylinder is equal to 200 meter cubic. The pressure inside the cylinder is 1 megapascal, and the temperature is 300 Kelvin. And the environment condition P naught equal to 100 kilopascal, and T naught also equal to 300 Kelvin. Okay, so because we know the system is closed system, in order to determine the exergy, so we need to use the exergy formula for closed system, which is referred to the formula for X and F. So X and F equal to M multiplied by psi, or equal to M multiplied by bracket what we call the internal energy difference, plus P naught multiplied by volume difference, specific volume difference, minus T naught multiplied by specific entropy difference, plus term for kinetic energy and also term for potential energy. So now in terms of specific internal energy difference, the value will be 0, U minus U naught. Why? Because we know that internal energy has a relationship with the heat and also with the temperature. So now for this condition, the temperature of the substance and also the temperature for the environment is constant. T equal to T naught equal to 300. So no internal energy difference involved. So U minus U naught will be 0. And let's say we ignore, because the system is stationary and the location of the system is at the datum, so kinetic energy will be 0, potential energy of the system also will be 0. Okay, so now we have simplified what we call the equation for X and F. So X and F equal to M mass multiplied by P naught multiplied by specific volume difference minus T naught multiplied by specific entropy difference. So now we need to determine the parameter inside the equation in order to determine the exergy value for this system. Okay, so in order to determine what I call the M, the mass, so we can manipulate, because the substance inside the cylinder is air, so we can consider air as an ideal gas. So we can manipulate whatever equation that can be used for ideal gas to determine the mass M. So we can use PV equal to MRT formula. So rearrange the equation, so we get mass equal to PV divided by RT, where R for a gas constant for the air equal to 0.287 kilojoule per kg Kelvin. So normally the value will be given. Okay, so substitute all the formula that we have. P equal to 1 megapascal, V equal to 200 meter cubic, R equal to 0.287, and T equal to 300. So remember that for this equation, for ideal gas equation, the temperature must be in Kelvin. Okay, so we have mass equal to 2323 kilogram of compressed air inside the cylinder. Okay, next we need to determine the term for P naught V minus V naught. Okay, so also we can manipulate the formula for P V equal to RT. So now, just now we use PV capital letter, so now we use PV V small letter, represent specific volume. Okay, the same formula, but we use the different unit for volume. Okay, so rearrange the equation, so we get specific volume equal to RT divided by P. Okay, substitute into the term for P naught V minus V naught. Okay, substitute in the V parameter and also V naught, so we'll get P naught V minus V naught equal to P naught bracket RT divided by P minus RT naught divided by P naught. Okay, take out the same parameter which is referred to the R and also T, because now condition is T equal to T naught. We just replace T with T naught, so that's why we can take out the parameter for R and also T naught. So we have now the term for P naught V minus V naught will be equal to RT naught multiplied by P naught divided by P minus 1. Okay, so now we need to determine the term for T naught multiplied by S minus S naught. Okay, so now to determine S minus S naught, we cannot obtain the value from the table, so we need to use the specific formula that we have learned when we learn about the entropy. So for entropy, under entropy chapter, we can find few equation that can be used. So we have two equation. First equation, we have S minus S naught equal to CV average multiplied by ln T divided by T naught plus R ln V divided by V naught. So we have S minus S naught equal to CV ln T divided by T naught plus R ln V divided by V naught. The second equation, we have S minus S naught equal to CP ln T divided by T naught minus R ln P divided by P naught. So we have S, second equation, S equal to S minus S naught equal to CP ln T divided by T naught minus R ln P divided by P naught. So we can use both equation in order to determine the value of S minus S naught. However, we need to make sure that we have enough information to use the specific equation. So for this case, the suitable equation is the second equation for S minus S naught, where S minus S naught equal to CP ln T divided by T naught minus R multiplied by ln P divided by P naught, because most of the parameter that involved with the equation we already obtained. Okay, so now simplify the the equation. So we will have T naught multiplied by S minus S naught equal to negative R T naught ln P divided by P naught. Okay, so we have this this simplified equation, because if you look in the bracket for equation where we have ln T divided by T naught, because the T equal to T naught, so T divided by T naught will be equal to 1, so ln 1 will be 0. So the term involved is ln 1 will be eliminated from the equation. So that's why we have this simplified equation for T naught multiplied by S minus S naught. Okay, so now substitute the equation for P naught multiplied by V minus V naught, and also equation for T naught multiplied by S minus S naught into the equation for X and F. Okay, as shown in the slide, and substitute all the data that we have. Okay, so we already have the data for R, the data or the value for M, T naught, P naught, P, and also P, so we can determine the value of X and F. And if we substitute all the value, so we'll get X and F will be equal to 280525 kilojoule. Okay, so this value actually represent the maximum amount of work that can be produced by this compressed air inside the cylinder in order to lift the piston upward. Okay, that's how we solve this problem for example 1.8. Okay, example 1.9, refrigerant 134A is to be compressed from 0.14 megapascal and -10 degrees Celsius to 0.8 megapascal and 50 degrees Celsius steadily by a compressor. Taking environment condition to be 20 degrees Celsius and 95 kilopascal, determine the exergy change of the refrigerant during this process and the minimum work input that need to be supplied to the compressor per unit mass of the refrigerant. Okay, now, so you need to identify the problem, whether the problem involved is open system or closed system. So if you look to the device that used in this question, the device involved is a compressor. So a compressor referred as a open system because the system will allow mass in and also mass out during the process. So we just draw a simple schematic diagram for the compressor. So we have mass in and also mass out to show that the system involved is open system. Okay, so put all the data given in the schematic diagram. So we have at the inlet, so we have P1, let's say we have inlet represented by number 1, outlet represented by number 2. So pressure at the inlet P1 equal to 0.14 megapascal. Temperature at the inlet, so the temperature of the refrigerant at the inlet T1 equal to negative 10 degrees Celsius as mentioned in the question. And the condition at the outlet P2 equal to 0.8 megapascal and T2 equal to 50 degrees Celsius. And the environment condition equal to 20 degrees Celsius in terms of temperature, and pressure P0 equal to 95 kilopascal. Okay, all this data are already given in the question. So you need to identify the data given is referred to the environment condition and also the inlet condition or the outlet condition. Okay, so now because we know that the system is open system, because the question asks you to determine the what I call the exergy change, so you need to use the exergy change formula for open system, which is referred to the delta XF, the formula that we have learned before. Okay, as shown in the slide. Okay, now because the system involved is refrigerant 134A, all the data that we need to determine to answer the question, we can determine by using the table. Okay, so if we use the symbol, the capital letter symbol of H and S, so we can determine the value easily. Okay, so the easy method is by using the the exergy per unit mass delta 5, which is equal to specific enthalpy difference minus T0 multiplied by specific entropy difference plus kinetic energy terms and also potential energy terms, where the value of H2, H1, S2, S1 we can determine by using the refrigerant R134A table easily. Okay, different from equation from the example of 1.8 when we discussed from previous slide, because the substance involved is gas or air. So in the formula involved is entropy value, so the entropy value cannot be obtained from the ideal gas table, so that's why we need to use the specific equation to determine the value of entropy for example 1.8. However, for example 1.9, all the parameters involved in the equation we can determine easily from the thermodynamic table. Okay, so now we ignore kinetic energy and also potential energy, so we will simplify the equation of exergy for exergy per unit mass, where delta 5 equal to H2 minus H1 minus T0 multiplied by S2 minus S1, and this value also represent the maximum potential of the compressor, which is referred as W in minimum, because we consider W in minimum because the system involved is the compressor. So we already discussed this term when we discussed about the difference between the compressor and also the turbine in terms of formula involved with exergy. Okay, so now we need to determine the H2 value, H1 value, S2 value, and also S1 value by using the R134A table. Okay. Okay, example solution for example 1.9. So first, we need to determine the phase for state number 1, the phase of the refrigerant 134A at the inlet of the compressor. So now you need to implement what we call your knowledge in thermodynamic 1 in order to determine the phase of the substance. So now, in order to check the phase, so you need to refer to the saturated R134A table by referring to the data given for state number 1 at the inlet of the compressor. So P1 equal to 0.14 megapascal, T1 equal to negative 10 degrees Celsius. So from the table, you need to determine the T saturated temperature at 0.14 megapascal. So if the temperature given T1 greater than T saturated, the phase will be superheated. But if the temperature of T1 lower than T saturated in the table, so the phase will be saturated, compressed liquid or subcooled liquid for the refrigerant. Okay, so now let me check. So from the table, we can see that at 0.14 megapascal, the saturated temperature is equal to negative 18.8 degrees Celsius. So now compare with the temperature given of T1 equal to negative 10. So negative 10 degrees Celsius is greater than negative 18.8 degrees Celsius. So T1 greater than T saturated at 0.14 megapascal. So the phase for the refrigerant at the inlet of the compressor is superheated. So now after we determine the phase, so we need to refer to the superheated vapor R134A table. Okay, to determine the actual H1 and also S1 value. So by referring to the same data for state number 1, P1 equal to 0.14 megapascal, T1 equal to negative 10 degrees Celsius. By referring to the superheated refrigerant 134A table, so you need to find out the what I call the table for pressure equal to 0.14 megapascal, and find out the what I call the line for, or the row for the negative 10 degrees Celsius. Okay, so from this table we can determine H1 and also S1, where from the table H1 equal to 243.4 kJ per kg, S1 equal to 0.9922 kJ per kg Kelvin. Okay, similarly with state number 2, first before we determine the value of H2 and also S2, we need to determine the phase of the refrigerant at the outlet of the compressor at state number 2. Okay, so we need to again refer to the saturated table for R134A based on the condition for state number 2, where P2 equal to 0.8 megapascal and T2 equal to 50 degrees Celsius. Okay, by referring to the table at 0.8 megapascal, the T saturated temperature is 31.33 degrees Celsius. So now compare with the temperature given of T2 equal to 50 degrees Celsius. So T2 is greater than, 50 degrees Celsius is greater than 31.33 degrees Celsius. So T2 greater than T saturated at 0.8 megapascal. So the phase for state number 2 is still superheated. So now we need to refer to the superheated vapor R134A table based on the same data of state number 2. Okay, find out the table for 0.8, the row for 50 degrees Celsius in terms of temperature. So then we can determine the value of H2 and also S2. So H2 equal to 284.39 kJ per kg, S2 equal to 0.9711 kJ per Kelvin. Okay, so now we already have the value for H1, S1, H2 and also S2. So the data already complete. So now substitute all the data into the equation for Exergy per unit mass for the open system for delta 5, where delta 5 equal to H2 minus H1 minus T naught multiplied by S2 minus S1. Okay, so substitute all the data that we have, so you will get delta 5 equal to 47.17 kilojoule per kg. So this is the value of Exergy change per unit mass. And the question also asks you about the value of W in minimum. So actually the value that you obtain for delta 5 or Exergy per unit mass also describe the value of W in minimum for the process, for the compression process in the compressor in this problem. Okay, that's how you solve the problem involved with Exergy for the open system in example 1.9. Okay, as I mentioned before, the outcome of the chapter number 1, chapter of Exergy. So the last section we need to determine the Exergy balance equation, isn't it? Okay, and the reference equation, before we obtain the complete Exergy balance equation, we need to refer the energy balance equation. So we have E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equal to delta E system. So in this question we have term for the energy transfer by heat, work transfer, energy transfer by work, and energy transfer by mass. So we have three terms. First we have energy transfer by heat, energy transfer by work, and also energy transfer by mass. And the last one we have energy change of a system. Okay, so now if we want to derive the Exergy balance equation, so we need to determine to consider the maximum energy potential. So when we consider maximum energy potential, so the energy balance equation will be the Exergy balance equation. So okay, so this is they call the intro of the Exergy balance equation. So we have similar pattern of Exergy balance equation if you compare to energy balance equation. So for Exergy balance equation also we have X in minus X out plus additional terms that we will learn later on, equal to, if you expand, equal to Exergy transfer by heat, Exergy transfer by work, and also Exergy transfer by mass. And we have additional in terms of Exergy due to losses. And the last one we will have Exergy change for different kind of system. Okay, so now we already derive in terms of Exergy change for the closed system, delta X and F, where delta X and F equal to M multiplied by bracket M multiplied by bracket U2 minus U1 plus P naught multiplied by V2 minus V1 minus T naught S2 minus S1 plus kinetic energy difference plus potential energy difference. And also we already derive the what I call the Exergy change for the open system, delta XF, where delta XF equal to M multiplied by bracket H2 minus H1 minus T naught S2 multiplied by S2 minus S1 plus kinetic energy different terms and also potential energy different terms. Okay, so we already solved the derivation equation for Exergy change, okay, for both systems. So in terms of value, delta X system in terms of value can be 0, can be positive, and also can be negative. And this depends on the individual value of Exergy for each state. For example, for the open system, the individual flow Exergy for each state is always positive. However, in the flow Exergy value can be negative if the pressure is below than the atmospheric pressure, where this require external energy source. Okay, this is what I call the summary. The summary that we have, that we already obtained for Exergy change in term of equation.